Dr. Ahmed. In this lecture, we will talk about the nuclear shell model to explain the structure of the nucleus and explain the behavior of the nucleons inside the nucleus. So, this lecture we have divided into two main parts. So, this is the first part of the lecture. So, let's start with the uh, nuclear shell model. Um, so at first we have to look on what are the assumptions of the nuclear shell model. That is, I mean, while we are making a shell model, so what should be the basic assumptions, or what are the basic assumptions one needs for the nuclear shell model? So the assumption that we have, the first assumption, that is each nucleus move in an average potential. I mean, this is the first assumption in a nuclear shell model, according to which each nucleus moves in an average potential. That is, I mean, it has a specific value for a potential as it moves at that particular potential. What it means that neutrons are the average of all nuclear interactions. So along with that, protons also see the same as the neutrons plus proton electric repulsion. I mean, so here we're saying that first we consider the case of the neutrons, and we're saying that neutron should observe, or neutron should see an average nuclear interactions. But when once we move toward the protons from the neutron, so we're saying that protons sees not only nuclear interactions, but also proton electric repulsions, because we know that in case of the neutrons we don't have electric charge, but in case of proton we do have the electric charge. So that's why unlike the neutrons, protons and additions can experience the proton electric repulsion as well. So the two potentials for the neutrons and protons are wells of some form, that is, nucleons are bound. Uh, each nucleus moves in single particle orbit corresponding to its states and the potentials. So this implies that we are making a single particles shell model. So here, when we say like this, I mean that we are saying that we are making a single particle shell model. So there is some basic questions one might have in mind. That is, why does this make sense? A nucleus full of nucleons and typical means for pre-path of nucleus scattering project. That is, I mean, consider the example of oxygen, which has a nucleus that is equal to 2 femtometer. So this is the questions one might have when we are saying that we are making a single particle shell model. So an answer, suitable answer for this question is because nucleons are fermions and stack up. They cannot lose energy and collision, since there is no state to drop into after collision. So this is the answer. That is, nuclear, they are being packed, they are being struck in a particular potential, so they cannot lose energy in collision. Why? Because there is no state to drop into after collision. You know that after the collisions, there are being states after which the particle they might drop, but in this particular case, there is no such state where the particle may drop after the collision. So we have to utilize the Schrodinger equations to compute energies. That is, I mean, we have to utilize the non-relativistic approach, justified by simple infinite square well energy estimates. And our aim is to get the correct magic number, that is shell closure, and uh, be content. So let's start. Let's start without thinking. I mean, we just need to compute. I mean, we're trying to make a shell model, but this shell models we're trying to make it without thinking. I mean, we just have to try some potentials. Our motive is, eat what you know. So these are the desired number. You can see it here. The desired magic number are 2, 8, 20, 28, 50, 82, and 126. These are the desired magic number. They can be either number of the protons, or number of the neutrons. It may be collectively the number of neutron or protons. And we are saying that with these numbers, the nuclei, they are relatively stable nuclei. So just now we're trying, so without any deep knowledge, without our shallow knowledge, uh, without thinking, we just are trying to put, our knowledge in account, that what we can get, what we can get. So the first step is we applying the Coulomb potentials. So in Coulomb potentials, we drop, uh, we plot the energy versus the Coulomb potentials, and by just putting the number, the numbers of the nucleons and the different shells, just like we have for the electrons. So the same we apply for the nucleon inside the nucleus. So when we plot the energy versus the Coulomb repulsion in the nucleus, so we get the values, that is for one is shell, we get 2. Similarly for the second 2s and 2p, we get the values 10, and for 3s, 3p, 3d, we get value 28. For 4s, 4p, 4d, and 4f, we get the value equal to 60. So you can see it here. Here we have only one value, that is 2, which is and match with the desired magic number. But other value, they deviate to 10, 28, and 60. They almost all deviates from the desired magic number. So when we apply the infinite square potentials, and we do the calculations, according to your knowledge, without thinking, applying our knowledge. So you know that here we get some of the magic number, some of the values, that's 2, 8, and 20. Along with that, these are the number which can make to somehow uh, with the desired magic number. But if we go beyond, so here you can see that all these numbers that deviates from the desired magic number. So what happened when we move to harmonic oscillators? So when the concept of the harmonic oscillators has been applied, so we can get the magic number. We can get accuracy in a magic number up to 3 magic number. That is, we can get 2, 8, 20. But again, if we go beyond, so again we see some deviations in the magic number. We're not getting the desired magic number. So that is, something we try uh, without thinking. We just trying to compute. So now, if you're trying the same thing with the deep thinking, with the proper knowledge, we know how the potential should look like. It must be of finite depth, and if we have short range nuclear potentials, then the average potential must look like the density that is played in the middle. You don't know where the middle is if you are surrounded by the nucleons. Uh, Steep at the edge due to short range nuclear potential. That is, you can see it by yourself. Here, you remember. This is the potential nuclear potentials according to Saxon War. So this is the relation for the potential. Here R in this relation is for the nuclear radius, and D is basically the width of the edge. So let's see what we have. Here, what we expect when we rounding up a potential well. When we rounding up a potential well, just like you can see it here. These are the potential well at different values of the L. That is, L is equal to 0, L is equal to 1, and L is equal to 2 for different values of the L. Here we have the question that what to expect when rounding up a potential well. I mean, and we are rounding up a potential as well. So what is our expectations? So our expectation is higher L solutions get larger angular momentum barriers. I mean, this is our expectations, that is higher L solutions get larger angular momentum barriers. What it mean? It mean that higher L waves functions are localized at larger R and thus closer to edge. This is the finding when we are rounding the edge. So rounding the edge effect, what it mean? Rounding the edge effect high L states. So most, because they are closer to the edge than low L1. So that is you can see it here by yourself. I mean that's how the things they are really happening. And so high L state, that is L Harvey means for the angular momentum. That high L states drop in energy because uh, it can now spell out across the edge, and this reduces their curvature. I mean, so here you can see that is higher L state. I mean, for the higher L state, drop in energy. Why is drop in energy? Because it can now spell out across the edge. So here you can see that it has spell out across the edge, and this reduces their curvature. So here you can see that that's why the curvature has been reduced. So and along with that, it also reduces their energy. So high L stage drop surrounding the well. Uh, so what actually we need to do? I mean, again, we're making a shell model with the thinking. So the well improvements, I mean, we have to apply the well improvement program. So by applying the sample harmonic, by applying the concept of sample harmonic oscillators, I mean, these are the magic number. That is the magic number. You can see it here. These are the desired magic number, and uh, these are the number we are expecting or we are getting with the harmonic oscillator. So how we can change or how we can modify or how we can improve this by applying the harmonic oscillator concept. So let's see. When we apply the harmonic oscillator, so we observe that harmonic oscillator or harmonic is bad. Wires being made, I mean, here you can see that, and then how we get the values. I mean, we see that each level has been split up in two or three or even four different levels. So even the elastic well does not match a magic number, so it need more splitting up higher L states. So what it mean that it should include a spin orbit coupling uh, at a low atomic number, and magnetic coupling much too weak and wrong sign. Two nucleons potentials has nuclear spin orbit terms. Deep and nucleons, its average away. So at the end, it has biggest effect. I mean, this is how when we apply the harmonic oscillators. So from the harmonic oscillators, we have the reasonable nuclear and reasonable nuclear plus spin orbit coupling, and then we get the accumulated occupancy. So the higher L, the biggest the splat. So this is all we have for. I mean, for the shell models, when we applying the concept of the harmonic accelerators with the deep thinking. So this is the first part of the shell models. It's all we have for this. See you with more detail in the next lecture. Till then, bye bye.